In my SPI video, I show you how to use the SPI peripheral on your microcontroller to drive 8 LEDs. In this tutorial, I will show you how to do the same thing but using I2C. So what I have done is I have bought the IO expander I2C version. Last time we were using the SPI version. So I'm controlling these 8 LEDs using only the 2 pins that the I2C protocol requires. So let's go check out the code. Let me go ahead and show you the schematic that I'm using for this application. So the name of the IC that I'm using is MCP23008. There's another version with the S in it instead of the first 0. This is the SPI version. So make sure that you buy the I2C version. This is the schematic. PA6 and PA7 from your microcontroller board are connected to SCL and SDA respectively. I have the I2C pull-up resistors at 4.7K. These are my LEDs. Your resistors should be 1K. The address bits of the IO expander are all connected to ground. The reset line goes to 3.3 volts. This is the location of the pins that we're using from the board. 3.3 volts, ground, PA6 and PA7. A quick I2C tutorial. We have 3 speeds, 100K, 400K, 1.7 megahertz. We will be using 100K. You have 2 lines, the clock line and the data line. Clock line is where you sample the data, which is on the rising edge, and how you send the data. And the data line is of course the line that contains the data that we're sending or receiving. An I2C connection consists of the 2 lines, clock and data, with 2 pull-up resistors. The value of those resistors depend on the speed that we're using. You can have more than one slave connected to the same bus. The master sends the specific address of the slave, so that's how each slave knows that the incoming data is for them and not for the other slaves. The steps are basically you send a start bit from the master. Since we will be operating in master mode, so we send a start bit. We send the slave address. We receive an acknowledge bit. But if we get an error bit instead of the acknowledged bit, then we have to handle that appropriately. Assuming that we receive an acknowledged bit, we then send the data. We receive another acknowledged bit for each data byte that we're sending. And when we're done sending data and receive the last acknowledged bit, we send the stop bit. In our case, this is how the data that we have to send looks like. So this is our start bit. We then send the slave address. These 3 bits are A0, A1 and A2. And if you recall, I have those connected to ground. That is why the value of them is 0. And these 4 bits are fixed, so they don't change. These are the only 3 that you can change depending on where you connect them to. So let me go ahead and show you which one is which. So the first one is A2, second one is A1, third one is A0. Then you send a read or write bit. We will be writing data to the IO expander, so our bit will be 0. In order for us to turn on an LED, we have to talk to the GPIO register, which is located at address 09 on the IO expander. And after we send the register address, we then send the value of the register. So I showed you how the IO expander works in my SPI tutorial, but just a quick overview of the register once again. This is the IO dir register. This sets the direction of the GPIO bits on the IO expander. So we first talk to this register, and which is located at address 00, and then we tell them that we want the GPIO pins to be outputs. So the value of that register will also have to be 0. And like I just showed you in the signal, once we have set the direction of the GPIO pins, we then set the value of the GPIO pins. GPIO register is located at address 09. And if we want to turn on an LED, then we set that bit to high or to 1. So in this example, all the LEDs connected to the GPIO pins will be on. The slave, after each of the bytes that the master sends, replies with an acknowledged bit. And the last bit that the master sends, or the microcontroller, will be the stop bit. But if there is an error anywhere in between, then we also have to send the stop bit at that point. So now that you know how the I/O expander works and how it is connected to the microcontroller, let's go ahead and check out the code. So what I have done is I have gone to the I2C section in the datasheet for your microcontroller. So this is the I2C sections, which is 16. If you go to section 16.4, there are some steps that show you how to configure the I2C peripheral. So what I have done is I have copied the steps for this section 1 through 12. Notice here, however, that this is to transmit a single byte. We need to transmit 2 bytes of data, not counting the slave address and the RW bit, which is another byte. But the data bytes are only 2, and these instructions are for sending only 1 byte. But if you go to the flowcharts section on the datasheet, there's actually a section with a flowchart for transmitting multiple data bytes. So my code is a combination of the configuration steps and this flowchart. So this is my code. First thing we need to do is we need to enable the I2C module. There are actually several modules. I will be using the I2C module 1. So if we go to the register where we select the module, we see that in order to use module 1, I have to set bit 1 of this register. So that is bit 1, and I'm setting it. Next, we have to enable the GPIO for the port that we're using. The I2C module 1 uses port A, since we're using pins PA6 and PA7. So this is how I enable the clock on port A. Let's go ahead and see this page. So port A is located at bit 0 on this register, and that's how you enable the port. In this line, we are telling the microcontroller that we want to enable the alternate functions for pins PA6 and PA7, and of course, since they are digital signals, then I enable the digital functionality for them. Let's go ahead and take a look at this table. So you can see how I know that I have to use PA6 and PA7. So in this table, you see the pin numbers, and what each of the pins do. So these are my I2C1. So this is the module number, that one right there, and this one. So that means that I can use these 2 pins for my I2C1 module, which are 24 and 23. And if you go to your pin diagram, Then pin 24 and 23 are PA7 and PA6. So that's how I know which pins I can use for I2C. The next thing we need to do is we need to enable the SDA pin for open drain operation. So that is the register for open drain, and we are enabling pin A7, PA7. Now we need to configure the PMCN bits. So let's go and see this table first. So in this table we can see that PA6 and PA7 have the I2C peripheral. Whenever we select the value of 3 for the PMC bits, so at each of these bits we have to put the value of 3 for PA6 and PA7, and this line is actually not required. So now that we know which value we need to put in the PMCN bits, let's go to this register. So PMC7, which corresponds to PA7, starts at location 28. PMC6, which corresponds to PA6, starts at location 24. So that is PA7. This is PA6. And I am putting the value of 3 that we got from this table at each of those locations. Next, we need to initialize the I2C as a master in this register. Remember that I'm using module 1 from the I2C peripheral. So let's go see the register MCR, which is the master configuration. So in order to enable master mode, we have to set bit 4 of that register. So that's bit 4 and we are setting it. Remember that we had different speeds for the I2C that we could use. If we want to use 100K, this is the instructions for that. So these instructions were taken verbatim from the datasheet. The only difference in our case is that our system clock is 16 megahertz. So if you go ahead and plug in that value in this formula, then we get a 7 instead of a 9. So go ahead and write a 7 to this register, and let's go ahead and check out that register MTPR. So that is our timer period, which starts at bit 0. That is why I have the value of 0 here. For step 8, I have decided to make 2 functions, set slave address and set RW. So to set the slave address, which is the address of the IO expander, if you remember, that was 20 hexadecimal. Then we go to this register MSA. So this is the MSA register. The slave address starts at bit 1. So that is my slave address, and I'm starting it at bit 1. And I have given it the value of 20, which is the value that I had here according to the datasheet of the IO expander. Now I have to set my read and write bit. So that is actually part of step 8. If I want to transmit data, which is what we're doing, then I set the value to 0, the value of the bit 0 in the MSA register. So put in a 0 gives us a transmit, put in a 1 gives us a receive. So that is my mode. If it's a 0, then I clear the bit. If it's a 1, then I set the bit. So I am doing a write, and that is why I have given it the value of 0 here. For steps 9, 10, 11, and 12, I have done the same thing. I made a function called write byte. So this is my function. The first parameter is the data byte that I want to send. The second parameter is the I2C conditions. I will show you what that means in a moment. So we have to place the data byte in this register, which is appropriately called master data. These instructions were also taken verbatim from the datasheet, so our values will be different since the instructions were for writing a single byte of data. We are writing multiple bytes of data. And let me go ahead and remove this comment since that was from me copying and pasting from some code that I had previously. So my conditions will go to the MCS register. If we go to that register on the datasheet, every time we send a byte or every time we send data through the I2C bus, we can select if we are, for example, if it's the first data byte that we're sending, then we have to put the bit of 1, which is the start bit, in as part of that data that we're sending. So remember, first we have to send the start bit. The slave address is actually sent automatically. So once we have configured the address using this function, we don't have to configure it every time. And so this byte, this byte here, so this is where we configure the slave address. We only configure it once, and that byte is sent automatically. So the only bytes that we have to create a signal for are the bytes following the slave address, which are to the register address of the IO expander that we're trying to access and the value of that register. And for the first byte that we send, we have to specify that is the starting byte. So that is the first byte. So we have to set the start bit on the signal. And this is a register where we do that. That is the control and status register. So that register has actually different values. So if you read from that register, then these are the values that you are reading. If you are writing to the register, then these are the values that you're writing. So like I said, for the first byte that we send, then we have to set the start bit, and we always set the run bit. So if we scroll down to the first time that I use the write function, this is the data that I want to send, and my conditions are run and start. So that is my first byte. That is my start condition. For the second byte that I send, which in my case for this application for the IO expander, the second byte is the last byte that you send. So I send my run condition as well as my stop condition. So we go to bit 2. That is the stop bit for my MCS register. So this is where I set my conditions. And so the first thing that we're doing is we are sending the address for the direction of the GPIO ports on the IO expander. Then we send the value. So the address of the IO there is 00. The value, we want to make all the GPIO pins outputs. So we send the value 00 again. If we wanted to make them inputs, we will send the value FF. So these two calls to the function form the first signal that we're sending to the I/O expander. After I have set my conditions, I wait until all the data is sent. If you go to this register, MCS, you will see that but don't go to the write only control register. Now we are reading from the register. So this is the section where we have to look at. So we're checking the bit 0, which is the busy bit, and that tells us if the I2C bus is busy, or if the I2C controller rather is busy. So we just wait until it's not busy anymore, and that means that the data was sent. We then check for the errors, and if we receive any errors, we handle those appropriately. So we receive an error, then we send the stop condition. If your controller lost arbitration, then you have to handle that appropriately. So if we go to MCS and we see bit 1, that is the error bit, and you can actually check which type of error you got. If you notice here, it says the error can be from the slave address not being acknowledged, or from the transmit data not being acknowledged. So this bit will tell you if the address wasn't acknowledged. This one will tell you if the data wasn't acknowledged. So inside this if, you could have another if that checks for which of those two bits failed. So now that you know how the write function works, let's go ahead and check what we have inside the while loop. So this is where I actually go ahead and control my LEDs. The register for controlling the LEDs is the GPIO register, which is located at 09 in my table for the I/O expander. And that would be the first byte that I'm sending. So I send the run condition and the start condition. Next, I send a variable that changes values, and that is what makes the LEDs change state. So this is the value of the LEDs, and it's a byte, and each of the bits in that byte represent the state of the LEDs, either on or off. And since that is the last byte that I'm sending for that specific transmit, then I have to set the run condition as well as the stop condition. And then I just have a delay so that you can actually see the LEDs change state, or else it will be so fast that you won't be able to tell that they are even changing state. So we didn't actually get a chance to examine the flowchart that I was showing you, so let's go ahead and do that right now. So in this section you have different flowcharts that you can use to do different applications. So if you're receiving data, then you can see how the flowchart goes. But this was a flowchart where I based my code on. So if you follow this flowchart and you follow my functions after or starting here, then you will see that I was following that flowchart. So it tells you which bits you have to write to the MCS register. Since this is the first bit that we're sending, notice that they're writing the run and the start bit. This is the while loop that I have in my functions, where I check to make sure that the data was transmitted. So that is a while loop where I read the MCS register, and this is my busy bit. So my busy bit is equal to 0. Then I continue reading until it changes. Once it changes, I check for the error. So this step in the diagram corresponds to my if statement here. If there's an error, then I go to this side of the flowchart. If there's no error, then I continue sending data. So this is the bit that you have to send every time you send data. And once you get to the last bit, which will be the yes in this flowchart, then you set the run bit and the stop bits. So that corresponds to me sending the conditions that I have in my while loop, which would be these right here. That's it for this video. Thank you for watching.